Now, this is obviously pretty interesting stuff. And what I really wanted you to learn here is how do you use vectorized approaches and vectorized thinking to effectively run really, really fast algorithms? Because what you see here is we have no loop in there whatsoever. So that's totally something different. Now, that's good and well, but as I said to you, the assumption here is that we have a normal distribution of our random numbers. So whatever random number we draw, it's always, the probability follows a Gaussian distribution, a Gaussian bell curve. But that's not really the case. And the question is now, what else can we do to perhaps mimic a more realistic distribution, right? And so one thing we can do is we can use our good old SPY returns, and instead of drawing samples from a normal distribution, we could actually draw samples from the original price curve. Yeah. So let's just say, we've got our SPY. Let me just see if it is still there. See, we have open, high, low, close. And so the first thing we want to do is we want to turn SPY into returns, right? So we want to do SPY.close. Do you remember what that is to turn it into returns?
Percentage change. PCT underscore change.
Correct. So we're basically turning this into a percentage change. And so what we can do now is we can actually, now we've got a vector of lots of percentage changes. What we can actually do now is we can plot a histogram. We can do this in pandas as well. We just go .hist bins equals 40. And so that's a histogram. Now look at the shape of this compared to what we had before. What do you realize? Look at this curve, yeah. Look at this one. Can you see the difference? Maybe we can just have a few more bins. Look at this.
I mean, it's definitely way less. Like, I mean, it's 0.025. Kind of like, what is the distribution, so to say, like the outliers. And
so yeah, the numbers here are not really important because before we just had random numbers. What's important is the shape, though. Look at the shape. So what you realize is it's actually a lot skinnier than the a bell curve would kind of look more like this. Yeah, it would just be less slim, like it would be a lot more broad. Yeah. But what also happens is, and we can't really see this here, there are probably quite a few like really, really far outliers, because you can see here the actual auto scaling goes quite far to the right. But there's probably some real outliers here that we can't even see on this chart because they're just so small. They're just like one. You can actually see, well, you can't really see that, but there's probably a few really sort of far outliers here, right? And this is actually what we call a fat-tailed distribution. So what that means is that it's actually, in a sense, skinnier in its body, but then the tails are wider. Yeah. So if we for example compare this distribution, right, and then we wanted a more fat-tailed one, the fat-tailed one would look a little bit like this. It would just go cut into here, then has a much higher body in the middle, and then falls off much steeper, but then ends up with much longer tails than this distribution. Yeah. So it's a different type of it's so what that shows us is that the actual distribution of stock returns is not normal. It's not normally distributed. What this distribution is actually something that a lot of academics discuss all the time. You can actually fit it quite well, for example, with a type of distribution. It's called a Cauchy distribution. But unfortunately, Cauchy distributions are not very well manageable mathematically. They're quite unstable. So they're not actually really useful for modeling. So otherwise you could just go, oh, I just model it with a Cauchy distribution. I use the parameter and then do it. But unfortunately, Cauchy distributions are not really mathematically stable. Now that's a whole nother story, but what I'm really trying to say is actually very difficult to model the distribution of stock returns accurately. Now, one way to get around this is to simply take the returns of this distribution and just draw samples from it, and then create new paths that follow this distribution, right? Mm-hmm. So in some ways, that's a good way of getting around some of the issues if you wanna get more accurate modeling of price or stock returns, right? And more accurate Monte Carlo simulations.